For biological purposes, the simplest form of a pure substance that retains all of the properties of that substance is an atom. Atoms are also the simplest form of an element. An element is made up of only one type of atom. For instance, carbon is an element. All carbon atoms look the same, and they are the only atoms that are carbon atoms. A different atomic structure would be a different atom, and therefore a different element. Consult a periodic table for a complete listing of the more than 100 elements. All atoms have three components: protons, neutrons, and electrons. The first element, hydrogen, has one proton, usually one neutron, and one electron. Hydrogen exists in nature as a combination of three isotopes, each of which has a different number of neutrons. Normally, the most prominent isotope, which has one proton, is considered. All hydrogen atoms, for the most part, look the same. What is ionizing radiation? Ionizing radiation is a form of energy that acts by removing electrons from atoms and molecules of materials that include air, water, and a living tissue. Ionizing radiation can travel unseen and pass through these materials. It's on the right side of the electromagnetic spectrum shown here. Higher frequency waves have higher energy and are more damaging. A familiar example of ionizing radiation is that of X-rays, which can penetrate our body and reveal pictures of our bones. Shown here is an X-ray of a child's mouth displaying both the milk or baby teeth and adult teeth ready to emerge. We say that X-rays are ionizing, meaning that they have the unique capability to remove electrons from atoms and molecules in the matter through which they pass. Ionizing activity can alter molecules within the cells of our body. That action may cause eventual harm, such as cancer. Intense exposure to ionizing radiation may produce skin or tissue damage. Other examples of ionizing radiation include alpha, beta, and gamma rays from radioactive decay. A radioactive atom will attempt to reach stability by ejecting nucleons, protons or neutrons, as well as other particles, or by releasing energy in other forms. Radiation is the energy or particles that are released during radioactive decay. The radioactivity of a material refers to the rate at which it emits radiation. Radioactivity is the property of some unstable atoms to spontaneously emit nuclear radiation, usually alpha particles or beta particles, often accompanied by gamma rays. This radiation is emitted when the nucleus undergoes radioactive decay and is converted into a different isotope, which may, according to its number of neutrons and protons, be either radioactive, unstable, or non-radioactive, stable. This daughter nucleus will usually be of a different chemical element to the original isotope. How much radiation am I exposed to? We are exposed to low levels of ionizing radiation every day. Ionizing radiation can fall into two categories: natural and man-made. Ionizing radiation from natural or background sources. Ionizing radiation that comes from natural sources is typically at low levels. This means that the usual amount of ionizing radiation from natural sources absorbed by our bodies, or dose, is small. These low levels of exposure vary with location, altitude, and type of building material used in home construction. You may also be exposed to the radioactive gas radon if your home or building has a leaky foundation. In nature, sources of ionizing radiation include space, cosmic or solar radiation, Earth, terrestrial radiation like radon, and building materials. Colorado has an especially high level of radon in the soil. Radon is a naturally occurring radioactive gas that comes from the breakdown of uranium in soil, rock, and water. It is invisible, odorless, and tasteless, and can enter homes and buildings through small openings or cracks in the foundation. Radiation can be found in any building, but private residences are the most concerning because that is where we spend most of our time. Ionizing radiation from man-made sources. Every day we use ionizing radiation to help us live healthy lives. Ionizing radiation is found in smoke detectors, used to disinfect medical instruments and blood, and to perform many other tasks in our daily lives. It is also a byproduct of nuclear power generation. Medical diagnostic exams are the main man-made sources of ionizing radiation exposure in the US. The goal of medical diagnostic imaging, like CT or CAT scans, PET scans, and X-rays, is for the benefits to far outweigh the risks. You can track the number and type of these medical diagnostic exams that you receive on a regular basis so that you can know your history and share this with your medical provider. Magnetic resonance imaging, MRIs, and ultrasound technology are examples of diagnostic exams that do not involve exposure to ionizing radiation. Mechanisms of radiation damage. Injury to living tissues results from the transfer of energy to atoms and molecules in the cellular structure. Ionizing radiation causes atoms and molecules to become ionized or excited. These excitations and ionizations can produce free radicals, break chemical bonds, produce new chemical bonds and cross-linkage between macromolecules, damage molecules that regulate vital cell processes like DNA, RNA, and proteins. The cell can repair certain levels of cell damage. At low levels, such as that received every day from background radiation, cellular damage is rapidly repaired. At higher levels, cell death results. At extremely high doses, cells cannot be replaced quickly enough and tissues fail to function. Tissue sensitivity. In general, the radiation sensitivity of a tissue is proportional to the rate of proliferation of its cells, inversely proportional to the degree of cell differentiation. For example, the following tissues and organs are listed from most radiosensitive to least radiosensitive: blood-forming organs, reproductive organs, skin, bone and teeth, muscle, and the least sensitive, the nervous system. This also means that a developing embryo is most sensitive to radiation during the early stages of differentiation, and an embryo or fetus is more sensitive to radiation exposure in the first trimester than in the last trimester. Immediate and delayed effects. Radiation effects can be categorized by when they appear. Immediate effects including radiation sickness and radiation burns seen immediately after large doses of radiation delivered over a short period of time. Delayed effects such as cataract formation and cancer induction that may appear months or years after a radiation exposure. Immediate effects. High doses delivered to the whole body of healthy adults within short periods of time can produce effects such as blood component changes, fatigue, diarrhea, nausea, and death. These effects will develop within hours, weeks, or days, depending on the size of the dose. The larger the dose, the sooner a given effect will occur. These acute effects apply only when the whole body is relatively uniformly irradiated. The effects can be significantly different when only portions of the body or an individual organ system are irradiated, such as might occur during the use of radiation for medical treatment. For example, a dose of 500 rem delivered uniformly to the whole body may cause death, while a dose of 500 rem delivered to the skin will only cause hair loss and skin reddening. Delayed effects of radiation exposure. Cataracts are induced when a dose exceeding approximately 200 to 300 rem is delivered directly to the lens of the eye. Radiation-induced cataracts may take many months to years to appear. Studies of people exposed to high doses of radiation have shown that there is a risk of cancer induction associated with high doses. The specific types of cancers associated with radiation exposure include leukemia, multiple myeloma, breast cancer, lung cancer, and skin cancer. Radiation-induced cancers may take 10 to 15 years or more to appear. There may be a risk of cancer at low doses as well. Why cancer risks at low doses are uncertain. It has been difficult to estimate cancer induction rates because most of the radiation exposure that humans receive are very close to background levels. At low dose levels of millirems to tens of rems, the risk of radiation-induced cancers is so low that if the risk exists, it is not readily distinguishable from normal levels of cancer occurrence. In addition, leukemia or solid tumors induced by radiation are indistinguishable from those that result from other cancers. Safety when working with X-rays. The main thing to remember when working with X-rays is to minimize exposure as much as possible. Newton's inverse square law determines your exposure to radiation based on your distance from the source. The basic formula is intensity, measured in rad, is equal to 1 over the squared distance from the source. To determine your exposure based on radiation of a known quantity, use the equation I1 over I2, indicating intensity, equals d squared 2 over d squared 1. In a clinical setting, lead aprons, walls, and shields are most commonly used to keep exposure to a minimum, especially to organs with rapidly dividing cells, like the thyroid and reproductive organs. According to the University of Colorado Boulder, no student, staff, or faculty may utilize X-ray irradiation in their research without training from the university. Therefore, the instructors will manage the X-ray machine while students will assist and observe. Please note that no student is obligated to be present during the radiation of the larvae.